Hello everyone, welcome to our e-learning classes for Naval Architecture. Hope you guys are doing absolutely fine, and today we are going to talk all about one of the most prominent phenomena regarding ship stability which ever takes place on board, free surface effect. The moment we talk about liquids, they have a tendency to flow since their weak intermolecular force allows them to do so. It simply means that liquids may acquire any shape they are kept in. As all of you must be knowing that a ship carries number of liquids in its various tanks for the purpose of its own operation. Everything in or on a vessel has its own center of gravity. The engine, the anchor, the ship's hull itself, your batteries, the cargo, and of course the liquid in your tanks. According to the weight and location, everything aboard contributes to the position of vessel's overall center of gravity. Heavier things influence the position of center of gravity more than light things. Off-center weights can pull center of gravity off the center line, causing the vessel to list. List means a permanent transverse inclination acquired by the ship. Let us now arrive on the concept of free surface effect. When a tank on board is not completely full of liquid and the ship heels, the liquid moves in the corresponding direction of vessel's inclination. Because of this, the center of gravity of ship moves away from the center line, which reduces the righting lever and also causes a virtual reduction in metacentric height of the ship. When in calm conditions, this is how liquid surface looks like. Representing the same on a two-dimensional plane would give us this. Ideally, we can assume it as equivalent to a straight horizontal line. In all of our upcoming diagrams, waterline will always be shown with a straight horizontal line. Since we are talking all about transverse stability of the ship, let's have a look on protection of the ship. The ship being floating on waterline WL, it is consisting of a partially filled tank inside. Because of some external forces, the ship will now heel in a particular direction. The liquid within the tank would also be shifting in the corresponding direction of vessel's inclination. The transference of liquid from one side to another takes place in the form of some triangular wedges, the wedges being called respectively as immersed wedge and immersed wedge. Just by looking at this diagram, I hope you get to understand why it is called as the immersed wedge and this one as the immersed wedge. Since a considerable liquid's mass has been shifted in a particular direction, this will also be causing center of gravity of the ship to move correspondingly in the same direction. Gravitational weight of the ship will now be acting downwards through new center of gravity G1. If we extend this line further upwards, this would be intersecting the center line somewhere. Now this vertical line makes an angle with the center line, so called angle of heel. This is theta. The ship has been assumed as floating with the displacement delta. Since your ship's hull may have a complex curvature throughout its length and breadth, that's why it is useful for us to take into consideration a small strip of the tank lying at a particular section, the length of that strip being dx, which is very small. Let us now have a look on geometrical dimensions of the tank. It is consisting of a half breadth of y. The center of gravity is of immersed and immersed wedges are lying at 2/3 of y measured from the tank's center line. Some more dimensions can be seen here. Just like this, we have as equals to y tan theta. Since the angle between initial and final waterlines, which we have here, is theta, shift in center of gravity, that is G(g)(1), is well determined by dividing moment of mass with the ship's displacement. So first we will be determining the liquid's mass in that particular wedge, and then we will be multiplying it with the respective distance covered by its center of gravity. To do so, first let us have a look on cross-sectional area of that liquid wedge. The area of this liquid wedge will be well given by half of base into height. It is simply half of y into y tan theta. Volume of that small strip having length dx will be further given by, like we will multiply it with 1 dx here. Further simplifying, it gets changes to half of y square into tan theta into dx. Now, how much will be the mass of liquid contained in that small strip? We will simply multiply this volume with the density of liquid which is being contained inside. The density being rho here. Now we are arriving on the moment of transfer of strip of wedge. Apparently this liquid wedge is getting transferred on the other side, and distance covered by its center of gravity in the upward shift direction is 4/3 of y. Let us just multiply the liquid's mass with this distance here. Simplifying further gives us rho into 2/3 of y cube into tan theta into dx. This expression gives us the value of moment of transfer of strip of wedge, means that small strip. In case we want to determine the moment of transfer of liquid in the complete tank, we will have to integrate this expression with respect to dx. In this expression, rho is a constant since the liquid which is being contained is ideal. For any particular angle of heel, theta will also be constant. Let us just bring rho into tan theta common outside of this expression. But we know that integration of 2/3 into y cube with respect to dx gives us the moment of inertia of liquid's surface about its center line. Finally, this expression gets changes to rho into tan theta into I. This is giving you the total moment of transfer of wedge inside the tank. In the expression of shift in center of gravity of the ship, this m into G(g)(1) will get replaced by rho into tan theta into I. Let us now have a magnified view of the ship's center line. Point K representing the ship's keel, center of buoyancy lying at point B, original center of gravity of the ship lying at point G. This will now go off the center line at point G1. Gravitational forces will now be acting downwards through new center of gravity, that is G1. Center of buoyancy after the ship inclines will also be changing its location. Upward buoyant forces will now be acting through new center of buoyancy. In this regard, we will then get the meta center here. Let us extend the vertical line through new center of gravity upwards. It will be intersecting the center line somewhere at point G2. Initially, the righting lever which we were having was GZ. Finally, it has just been reduced to G1Z. Now, it comes a very interesting part right here. The ship's weight either it acts downwards through point G1 or it acts through point G2. We are going to have the same amount of righting lever in both the cases and hence the same stability behavior of the ship. That's why it is an assumption that the existence of free surfaces within the ship will be causing a virtual rise in ship's center of gravity, right from point G to point G2. Or we can also say that there will occur a virtual loss in metacentric height of the ship equals to GG2. The ratio of GG1 and GG2 will be giving us tan theta. We can alternatively say that GG2 is equals to GG1 divided by tan theta. But earlier we have studied that GG1 was equals to rho tan theta into I upon delta. Now tan theta will get cancelled from numerator as well as denominator. Finally, the expression for GG2 which we will have here is rho into I upon delta. This expression will help you out in the determination of virtual loss of metacentric height because of existence of any free surface within the ship.